In this tutorial, I want to have another look at worked example 1, where we solved an integral by using the technique of integration by parts. Now, integration by parts uses this formula here. It relies on the fact that we transform the integral we can't do into an integral we can do. It relies on the fact that u, and if we trace u's journey through the equation, we've got a u here, we've got a u here, but we've got a du here. So if we choose u such that du is simpler in algebraic terms, it makes this whole second integral simpler, and we can solve the original complicated integral. So the choice of u is crucial. If we choose e to the 2x as u, we would get e to the 2x, e to the 2x, then the differential of e to the 2x here, e to the 2x remains as part of the integral. So the second integral is just as complicated as the first. However, if we chose x as u, we have x here, we have x here, and we have 1 here. So this second integral just becomes the integration of v. So let me very quickly go through the solution of this integral, then I'll show you a really fantastic method and layout for doing a more complicated integration where we actually have to go through the routine twice. Let's just do this one and you'll get an idea. So we chose u is equal to x. We need du dx, and that's equal to 1. So if we choose x as u, this must be dv. So dv dx is equal to e to the 2x. So v is equal to the integral of dv dx, and that's equal to the integration of e to the 2x is e to the 2x multiplied by a half. Again, if that's complicated for you, you're going to have to look back at the previous example or even go back into differentiation where I look at the chain rule, because this is an application of the reverse chain rule. So putting all this together, we get the integration of x e to the 2x is equal to uv u x multiplied by v, which is a half e to the 2x, minus the integration of v, which is a half e to the 2x, multiplied by 1. And this is equal to a half x e to the 2x. And the integration of this, well, the half can sort of be outside. And if you just look at e to the 2x again, well, we know the integration of e to the 2x, it's half e to the 2x. So the two halves multiply together to be a quarter e to the 2x plus c. And that's the answer we took forward and solved the rest of the question with. So what's this fabulous method? Well, this fabulous method comes into its own when you've got an integral which is slightly more complicated. Supposing our integration was the integral of x squared e to the 2x. So we'd still have to choose x squared as u. Du dx be equal to 2x. So let's see how our integral would work out. The integration of x squared e to the 2x would be equal to, obeying the formula, u times v, u, x squared, times v, well, v would be here because it's the same term, so this is multiplied by a half e to the 2x minus the integration of v du, v, again a half e to the 2x multiplied by du 2x. And if I just tidy that up, we've got a half x squared e to the 2x, but we've got a second integration here. Yes, the 2 will cancel with that 2, leaving us with the integration of x e to the 2x, which in itself is another application of integration by parts. We'd have to say this is a new u and this is a new dv, and apply the formula again. So you can see this process of going around the whole loop twice becomes very messy. Now I'm going to show you a method using a table that can do all this work. You get all the integration and the differentiation over in one go, and then you can just read off the answers. And I'm going to show you this method using this integral here, for which we've done, I must say, quite a lot of the work. So forming that table won't be an arduous task at all. So there's a table, sort of 3 along, 3 deep. As before, we start with our choices of u and v. This guy's going to be u, and this guy's going to be dv. So you name your first column u and your second column dv. So we might as well pop in our choices for u and dv. So this is x squared, and this is e to the 2x. This first column is going to be signs, not the trig variety, but just the plus and minus variety. And we've got a positive integral here. So I'm going to write a plus there. And all I do is alternate down the column as far as I need. Plus, minus, plus, minus, plus, minus. You'll see how that comes in very useful later. So let's sort out this first column. Down this first column, I'm going to differentiate. So each new row will be the differential of the row above. So this is 2x, this is 2, and this will be 0. You differentiate down until you get a 0. And you won't be surprised in the second column, when we go down the rows of the second column, we integrate. Let's fill in these. This is the hardest part of this method, to just do these differentials and do these integrals. The integral of e to the 2x will be e to the 2x multiplied by a half. Again, look back if that was a mystery to you. Integrate this again, we get a quarter. E to the 2x. And integrating again, we get an eighth. E to the 2x. Because we're only concentrating on one thing at a time, this is really easy to do. Now we've got to gather up the results. What does the formula say? The formula says u times v. Well, this is v, because our first integration, which started off with dv, this turns into v. So I need to multiply these two guys together. But I also need to take the sign of the term with me. So in a way, we've got a double-headed arrow, plus x squared multiplied by a half e to the 2x, and it produces our first result here. Our first result is plus a half x squared e to the 2x. Well, our next result is formed by exactly the same white arrow route, but a line down. What do we get from this multiplication? So it's negative 2x multiplied by a quarter e to the 2x. So that will be the second term in our answer. Well, we need to do it again. So another series of white arrows. So what do we get here? We get plus 2 times an eighth, which is a quarter, e to the 2x. Why have we stopped there? Well, the next series of white arrows, which start here, will involve the multiplication of the terms by a 0. So whatever the terms are in the next row down, which I didn't bother with, the result will be 0. And that will continue to be true all the way down the table, because the differential of 0 is 0 again. So we've reached the end. So what's our answer? Well, our answer is the addition of all these 3 lines. So this column really is results. So I can say that the integral of x squared e to the 2x is equal, better come down to another line here, this term here, which is a half x squared e to the 2x. Then this term, is it simplified enough? No. The 2 can go into the 4, leaving 2. So this is minus a half x e to the 2x. And the last term now plus, and this will be a quarter e to the 2x. plus c if we have no limits in this case, and that is your answer. I think that's a brilliant method, and it saves that reallocation of a new u and a new dv when you go round the loop for the second time. You get all the pain over with in one go. In other words, you do all your differentials and you do all your separate integrals. You get them out of the way. And the great advantage is you see the pattern. Look at the pattern. E to the 2x is always there. On the first line, it's a half. Then you multiply that by a half, and then you multiply that by a half again. So there's much less chance of making a mistake. Then all you've got to do is remember the white arrows, which tell you which terms to gather up in accordance with the formula. U times V is the first requirement. U is here multiplied by V. Answer. Then the next lines, you see, work out the second integral, where you have to go round the loop again. And you gather up those terms along the second row of white arrows. Negative 2x multiplied by a quarter, e to the 2x turns into the second term. Then the white arrows for the third term. Now positive again. That's why you have this alternating sign on the first column. It's a really good way of doing these multiple loop integration by parts.